Hello friends, in this video we are going to discuss about the band diagram of different materials. So before going to the intrinsic, N-type and P-type semiconductor, let us see what will be the band diagram for an conductor, semiconductor and insulator material. Then we will go for the intrinsic N-type and P-type. So for the conductor material, we know that the conductor materials are those materials in which the current can conduct at any condition. That means there will be a large amount of free electrons. That's why they conducts the current. So in conductor, the band diagram looks like this. There will be conduction band. So this is my conduction band of the conductor. So we can say the minimum energy of the conduction band is EC, and the valence band will be there. There will be valence band like this. So if I say this is the valence band, so I can say this is the valence band, and the maximum energy of the valence band is EV now. So we can see that there is a overlapping of valence band and conduction band. This overlapping area consists of large amount of electrons, free electrons, which will help to conduct current for the conductors. So we can write that for conductors there will be overlapping of conduction band and valence band. Now let us discuss about the insulator band diagram. So in the insulator band diagram, there will be a conduction band. So let us define that this is the conduction band. So I am defining it as conduction band or CB. So the minimum energy of the conduction band will be EC, and there will be a valence band. Suppose this is the valence band, and this is the maximum energy of the valence band EV, and this is the valence band VP. Now the energy gap between, or the energy band gap, is denoted by Eg, and this energy gap is greater than nearly 5 electron volt, nearly 5 electron volt or 4 electron volt. So we can see that the energy gap between the conduction band and the valence band of an insulator is very high, that is 5 electron volt to 4 electron volt, greater than 5 electron volt to 4 electron volt, and all the valence electrons will be residing inside the valence band in this way. That's why there will be no electrons, that is the no free electrons inside the conduction band. That's why the insulator cannot conduct current, because its conduction band is empty of free electrons, and these electrons cannot jump into the conduction band. That's why insulator cannot conduct current due to the unavailability of free electrons. Now let us discuss about a semiconductor material. So for semiconductor material, if we look at the band diagram, it will look like this. There will be a conduction band. So let us assume that this is the conduction band and this is the EC energy. So I am writing it as conduction band. Now the energy gap of the semiconductor is nearly this one. It is very smaller than the insulator, that is Eg value is less than 4 electron volt. So this is the valence band and the maximum energy of the valence band is Ev. So we can see that for the semiconductor materials, the energy gap between the conduction band and the valence band is very much small, and at t equals to 0, let us consider at t equals to 0. So at t equals to 0, all the valence electrons reside inside the valence band in this way. Now, if I raise the temperature, suppose I am raising the temperature beyond 0 Kelvin, then what will be done? The electrons here will move or jump into the conduction band and there will be a free electron. Similarly, other electrons can also jump into the conduction band because the energy gap here is very small. So a hole will be created here. Similarly, a hole will be created here. So now we can see that a free electron will be created at the conduction band. And now the semiconductor can conduct current at temperature greater than 0 Kelvin. So this is the band diagram of a semiconductor and this is the band diagram of an insulator. Now let us go for the band diagram of an intrinsic semiconductor. So we are writing the band diagram for intrinsic semiconductor. Then we will go for p-type semiconductor. Then we will go for n-type semiconductor. Now in the intrinsic semiconductor, the conduction band will be there. So let us assume that this is the conduction band and this is the EC energy level. Similarly, let us assume that there is a valence band and this is the EV energy level. Now, for intrinsic semiconductor, the Fermi level energy will be nearly at the middle of the band gap. So this is the Fermi energy level of the intrinsic semiconductor and EFI will be nearly at the middle of the band gap, that is Eg. So the band gap will be this one, this is the band gap Eg, and the EFI will be nearly at the middle of the band gap. So this is the not exactly at the middle of the band gap but nearly at the middle of the band gap. Now For the p-type semiconductor, there will be similarly a conduction band. This is the conduction band and this is the valence band. So this energy level is EV, this is the EC, and we can define that this is the middle of the band gap. So middle of the band gap can be defined by Eg by 2. So in this case, the Fermi level of the p-type semiconductor will be near to the valence band. So this is the Fermi level of p-type semiconductor. Now, if we define the band gap or energy band diagram for the n-type semiconductor, so there will be a conduction band similarly, and this is the EC energy level. Similarly, we'll have a valence band. So this is the valence band and this is the EV energy, and let us define that this is the middle of the band gap, that is Eg by 2. Now the Fermi level for the n-type semiconductor will be near to the conduction band, that is the EF n will be near to the conduction band. So we can say that the Fermi level, that is EFP, will be near to valence band and EFN will be near to conduction band. So this is all about the energy band diagram of intrinsic, p-type and n-type semiconductor. Thank you.